So
Yes,
our high
I'm good.
power.
Yeah, yeah.
So tell me about the low power techniques. Tell me about the low power techniques.
So there are different low power techniques we use. Um, First of all, we have voltage scaling, frequency scaling. First one is voltage scaling, frequency scaling, and using multi-voltage, multi-VT cell, using multi-voltage domain, and
Hmm.
using multi-voltage domain, multi-VT cell, power switch, retention cell, and isolation cell. So these are the different low power techniques we use in our design.
Hmm. Tell me about the diagram also. Tell me the
Yeah,
name.
yeah,
Around 7-8 techniques are there, right? 7 to 8
yeah, yeah.
techniques are there.
Yes, so I will share my screen. I will little bit explain you about all
Yeah,
these
one by
techniques.
one you can share. One by one you can tell and make the diagram also. So or formula, whatever it is required, right? You
Yeah,
can take
yeah,
your
sure.
time. No, no time.
Sorry.
You can take your time and one by one you
Uh,
can tell all the techniques, whatever you know.
Okay. So we have different low power techniques. Here, if I explain you here, so one one we have voltage scaling, frequency scaling using multi VT cells. First, I will list down all the low power techniques, then I will explain you one by one.
Yeah.
Fourth one is using multi voltage domain. Fifth one is using a retention cell. Isolation cell, using isolation cells, using level shifter, clock gating, data gating, and we have this power gating. So these are the different low power techniques that we use. So if I talk about the first one, the voltage scaling. In the voltage scaling, we dynamically adjust the voltage supply voltage according to our workload or like our requirement. Similarly, frequency scaling. Depending upon the workload or requirement, we scale the frequency at the runtime. So what happens?
Okay.
So yes.
You
So
can
what
tell me the range also of the voltage at the first method. What will be the range of the voltage?
So the range of the voltage depends upon the workload or requirement. Uh, so and similarly for the frequency also. For example, if we are scaling our dynamic power, and these are used to voltage scaling and frequency scaling are used to adjust the dynamic power. So we know our dynamic power. This is dynamic power is direct is like proportional to our we have alpha
Hmm.
c
Hmm, hmm, hmm.
e square into f frequency. So our dynamic power is directly proportional to square of the voltage and frequency. Now if we reduce the voltage supply voltage, if we reduce the supply voltage, then our gates will become slower, and if the gates become slower, then means the delay will increase. If the delay will increase, and if the delay will increase, um, our as the delay increases, our circuit will become slower. So we need to scale down the frequency also to match the timing requirements. Otherwise, timing requirements will not meet. We will see some timing violations. So therefore, frequency should also reduce. So now what happens if frequency reduces? Our performance will also reduce, right? We cannot operate on high frequency, right? So these things will like there is a trade-off between the power, performance, and area. If we want to achieve the low power, there is a trade-off with the performance or the area. Now similarly, if we reduce the frequency, right? Next case is if we are reducing the frequency, then what happens? The delay will increase. And we need to scale down the voltage also, because uh, like if we are reducing the frequency, it means delay increases. Means the voltage can also come down to match the requirement, right? So this is how these things are handled. Now if we talk about the next one, the multi-VT cell. So in the multi-VT cell, suppose we have this is a launch block, this is a capture block, and this is the clock. And this is a combination logic is there. The data is going like this. Now what happens if we see the setup slack? T clock plus L2 minus T setup minus L1 plus TCQ plus T combo. These are the equation of our setup timing. Now what happens if this is a critical path, right? Here the cell we are using, this is a VT, means the threshold voltage is there. Now if we will reduce the T combo, right? We want to reduce the T combo, and it means what happens, the setup slack will increase. They want to increase the setup. There might be some violation in the setup violation might be there. So if the setup violation is there, we need to increase the setup slack. So we are to increase the setup slack, what we can do on the RTL level, we will decrease the T combo, right? So to reduce the T combo, if we have 2 VT, right? Now if the VT is high, it means if the VT is high, this is the current. Delay and speed. So if the VT is high, it means the current is low, right? If VT is high, current is low, and current is low, it means delay is high. And delay is high, it means the speed is low. So here now we are speed is low, it means the T combo is high. So to reduce the delay, we will use a fast switch. So how we can use fast switch? If the speed is very high, speed is high, it means it will consume more current. It will consume more current. Current will be high, delay will be very less. So it means current is high, it means we need to take low VT cell. So this is how we can switch from we can use multi VT cell depending upon the requirement. But what happens if we are using low VT cell? It will consume more current. Speed is very high, but it will consume more current. It means the IR drop will be high, and I square R drop will be high, and it will consume more power. So there is a trade-off. We can see if we want to improve the performance, we want high-speed cell, we want our circuit to work on high speed, then there will be a trade-off. It will consume more power.
Hmm.
And now let's go to the fourth, multi-voltage domain. We can use the multi-voltage domain so that like there are different subsystems or different blocks. The different blocks are working at different voltage. The requirement is like that. So what happens? These are the different blocks working on different voltage domain. So instead of supplying same voltage to all the blocks, we can use different voltage domain. Like this
Hmm.
block is working on voltage 1, this block is working on voltage 2, this block is working on voltage 3, like that.
Okay.
So, so these kind of things we can do to reduce the power. And another one is
And
retention cell.
also, it have some disadvantage. It have some disadvantage. Multi voltage domain.
Yeah,
Any advantage in that?
disadvantage. Yeah, so disadvantage we can see like if we are using multi-voltage domain, so we need to add lever shifter in between. So the function of lever shifter we write it is not part of RTL, but in UPF this lever shifters are used. We can define the power intent and the lever shifter. So what happens? The function of lever shifter is if the signal is going from low voltage to high voltage, it will balance the voltage between the both. So if signal this is coming from voltage 1, so the lever shifter will rise the voltage as per the destination voltage domain. So the signal will have the voltage 2 here, like that.
Okay. Okay.
So disadvantage of multi-voltage domain is the we need to add some extra logic like this. We need to add
Okay.
some extra logic like a retention cell, level shifter. These are the level shifter, and retention cell is uh, so it will eventually increase a little bit amount of area will increase, and due to the level shifter, a little bit amount of delay will be there. Delay will increase or area will increase. So these are the things. And the what is the function of level shift? This is the level shifter. The function of isolation cell. So, for example, uh, yes. So let us assume that this is the isolation cell, and this is the this is a gated domain. Okay, this is the gated domain, and this is the always on domain. So now what happens if some signal is going from gated domain to always on domain? Suppose this thing, the gated domain has been turned off, but the signal should go from here to here. If this gated domain is turned off, then this signal is zero, and the aon domain always require that input. So what will happen that input will go to the some metastable condition, or it will not define any value because it is coming from the gated domain. Here everything is turned off, right? We need to give some at least some value we need to give as an input to our aon domain. Now the function of the isolation cell is it will clamp that value to either 0 or 1, that what we need to give any value. So this will clamp the value to either 0 or 1 if any signal is going from gated domain to the aon domain. Uh, so this is the function of isolation cell. Now next one is retention cell. So retention cell sits inside the gated gated power domain. So whenever everything is turned off in the gated domain, some critical signals are there, they need to retain their value. If we are turning off everything and some critical signals are there, they need to retain their previous value. So how can we do that we can do with the help of retention cell. Whenever the domain is turned off, some critical signal, they will retain their previous value with the help of retention cell, and retention, they have the different supply, that is only retention supply. So these things are there. And next one is clock gating, data gating, and power gating. So yes,
Okay, so till now you have told me five things, right? So
yes.
how to implement the 1, 2, 3, 5? Like have you used these in your article code? Have you used any one of these in your article code?
No, I have not used any of this, but I was responsible for handling. There was one block was there, which is called DCVF. Uh, it means dynamic clock and voltage scaling. So I have not written the code, but I was responsible to handle that particular block. I understood the functionality. Uh, this I identified and resolved some of the critical functional issues, and like enabled early release of the RTL for the DCVS block.
Mm-hmm.
So in the DCVS block, there is the low power technique we used was voltage scaling and frequency scaling. So that I have done.
Okay, okay. Can you drive the low power techniques formula, including the short channel effect? Can you
Can
write
you?
the formula power
Uh,
techniques? Complete power technique, power equation. You can write the power equation, which include the short channel, short circuit power.
short circuit
Can
power.
you have to write the complete formula of the power, which include the short circuit power.
Okay.
You know about short circuit power or not?
Yes, I know about short circuit power. So short circuit power is actually the power dissipation whenever our CMOS is switching from 1 to 0 or 0 to 1. So whenever at the time of switching, a short circuit current will directly go from the supply voltage supply to the ground, and there and for that short duration of time, the high amount of current will flow, which is called short circuit current. And the power loss due to the short circuit current is short circuit power.
Okay, okay, fine. So,
Yeah, regarding the
you know the formula of that. You know the power
uh,
formula of that.
no, I am not
Okay,
aware
fine.
of.
So when the circuit power dominant, you have any example when it is dominant? You have any condition?
Yes, so short circuit power is dominant whenever your CMOS is switching. So at the time of switching, let's say our CMOS is switching from 0 to 1. So it means that time our PMOS will be 0 and NMOS will be 1. Now when it switches like this, if I here this is ground. This is VDD supply, and this is ground, and this is our output. Okay. Now and this is gate voltage. Now whenever initially, let us assume this is 0. So output, this was 0, this was 1, and output was equal to 1. Now whenever we switch from 0 to 1 at a short for a very small amount of time or short amount of time, Now this will become uh, yeah, this will become 1 and this will become 0. Now, for a very short amount of time, what will happen? Both will be on. Like here, earlier NMOS was blocked and PMOS was transparent. Now, when it switches, VG switches from 0 to 1, NMOS is 1, which is transparent, and PMOS is 0. But for a very short amount of time, both will be transparent and current will flow directly from here to ground. And this is called this is called short channel current. And due to this current, the power dissipation will be there, and that power dissipation is called short circuit power.
Okay. Okay. Oh, why does the lowering the VDD not
Mhm.
always reduce the power significantly at lower nodes? You know about this thing that always if we reducing the VDD, it is not significantly lowering the power at the low advanced node. Although we have the formula like V square is there, so why
Correct.
it
Yes.
is so?
Uh, we actually, I'm able to remember the graph.
Mm-hmm.
If I draw like this, like this. This is the nodes,
Mm-hmm.
and this is the voltage graph, and this is the frequency. So as we go towards the lower nodes, uh, this I'm not able to remember exactly.
No problem. No,
Yeah, can
no, no,
you?
no. I will share the
Can,
questions with you later. Fine, you can just research it once. Fine. Fine. I will share the
uh,
questions also.
okay, okay, yeah, sure, sure.
Yeah, this interview will be completely on low power. This round will be on low power only.
Okay,
Uh,
okay, yeah.
Explain the trades off between the leakage power and dynamic power at lower nodes at let's say 5 nanometer technology. Trade off between leakage power and dynamic power.
Okay, okay. So uh, at lower technology nodes,
Yeah.
okay. So at high frequency, what we So we know the dynamic power. Dynamic power is equal to our P alpha C V square into F. And to reduce the dynamic power, we use voltage scaling and frequency scaling we do generally, right? So these are the techniques. In case of leakage power, to reduce the leakage power, we do either this power gating. Some techniques we use the power gating and using multi-VT cell. So if we are using multi-VT cell like this, depending upon the path, if VT is reduced, it means the VT is reduced, uh, then current will increase. So now what happens if current is increased? It means the delay is reduced, and now we can operate on the higher frequency. The frequency is increased, right? Now, as the frequency increases, we can operate on a higher clock frequency. So our this frequency is increased, and dynamic power will also increase, right?
Mm, mm.
So by reducing the VT, we try to reduce the leakage power, but so actually high frequency is running on high frequency, and
Okay, you know power formula. Power formula, you know.
power formula for what?
Power formula, complete power formula, you know. Complete
Uh,
power formula is alpha half CV square F plus
okay,
ISC. ISC means short channel effect into voltage plus I leakage into voltage. So this is a complete formula.
okay, okay.
You can write it also. That I asked in the first question, fine?
Yes, yes. Complete power formula.
Uh, okay, next question, going to the next question because a lot of questions are there. Do you know
Okay,
about
okay.
stack effect? Stack effect, you know, stack effect. STACK effect. Stack effect.
Stack effect. I'm not very sure, but I've heard this thing. Um, so as we do the stacking, like as per I'm not very sure, but as per my understanding and knowledge, what I know that if we do the stacking of the moss, then it will impact our current and performance. I'm not very
Okay.
sure with that. Yeah,
Basically,
yeah.
when multiple of transistors are in the series, immediately node voltage rises and VGS and VDS reduces and leakage power reduces exponentially. So this is the power explanation they are given. I will share the
Uh,
questions and answer also later. No problem.
yeah, yeah, sure, sure, sure.
Okay. Mm, okay. Tell me about the next power technique. You know, like you have explained to five, I guess, right?
Yes, yes. So the
Yeah, you can explain that.
next power technique is this. I've explained till the level shifter. So we have clock gating, data gating, and power gating. And so in case of clock gating, yeah, we use here. Can you can see my screen, right?
Yes, yes, yes.
So in case of where we use the clock gating, suppose any block is there and it is not functioning for a particular amount of time, but clock is still going. So it means toggling will be there in the clock and it will consume a lot of amount of power. So we do clock gating so that for a particular amount of time, if the block is not functioning, we'll stop the clock for that amount of time to reduce to save the power. And for the clock gating, we use the ICG cell So this is the ICG cell. This is a special type of cell we use for the clock gating. Why? Because if we use normal AND gate, so there will be glitches, and there will be a chopping of clock, and glitches will be there. So this special kind of cell we use, it is also called a glitch-free clock gating. So this is the if I draw the waveform also, this is the normal clock. Now here I will draw that ICG cell. This is enable. This is clock. Now this is the clock and this is the enable. Let's say enable switched on here. Now what happens? This is enable and this is enable latched. L. So this will this now here if we see our enable latch is one here, but still we will see the output of the clock like this, because here now this clock is zero here. Here this is zero, and here we have one. So output of AND gate will be zero, and it will be like this. And now from here we will get the clock. So there, this is the clock at the output we are getting. It is a glitch-free clock. So therefore we use clock gating with ICG cell. And the next one is the data gating. So in case of data gating, it depends upon our the functionality, that what functionality we want to use. So for example, if I give you one example, let's say here some mux is there, right? And here we have mm, yeah, one block is there like this, one more block is there. Now this is A, this is B, this is select line, and this is 0, this is 1. And let's say this is multiplier, and some heavy computation is going on, and this is simple logic like adder is there. Now if the select line is 1, it will select the multiplier, and if the select line is let us take this is x, and if the select line is 0, it will select the adder output y. But if let us select line is 0 now, and output is y, but a and b both are going here, right? Both are going in the multiplier, and there will be a toggling will be there, multiplier is still functioning, but our mux is only selecting 0 at that time when select line is 0. So we can see the toggling will be there in these two lines, multiplier is still functioning, so it is consuming lot of amount of power. It is performing some heavy computation task, it is doing something. We don't want this. So how we can do, what technique we can use here? So what we can do, instead of doing like this, we can put some small gates we can use, and gate like this. So now whenever the select line is 0, it means A and B will not go to the multiplier, and this multiplier will not function, and the amount of power will be reduced. So this is how we can ensure that data gating is properly utilized, and amount of power can be saved. And
Okay.
yes, and the last one is power gating. Power gating generally we do in the UPF command. So if I write the power gating in the UPF, the command we use is the create power switch. We'll write the name of the domain, and we'll write the input supply port, output supply port, create power switch, domain, input supply port, output supply port, and control port. So this is a low power technique we use with the help of power switch. And in power switch, if some domain is not functioning, so it is not functioning, then we'll gate the power supply to that particular block, so that leakage power should reduce.
Okay. 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 So have you implemented your power technique or crow getting technique in your RTL design? Have you used it? UPF?
No, I have not used, but I worked with the low power team and like got the basic knowledge of the low power techniques, and like what are the basic UPF commands we use. So these type of like basic knowledge I got. I have run the CLP tool to generate the reports. Uh,
Okay.
these type of things I help collaborated with the low power team, and like learned these type of things.
Okay. Fine. So how you decide the partition of the power domain in a large SOC? How you decide? You have any approach for that? Like how you decide the power domain, partition of power domain in large SOC?
Okay. So in a large SOC, some we need to check that which are the blocks that are working that according to their requirement. What are that blocks that are working on the different power, like what is the voltage requirement for them, what is the frequency requirement for them, and what is the power requirement for them. Are they consuming high power, or they are working at high frequency, or there might be some blocks which the requirement is there, they are working on low power, they are not performing that much heavy computation task, they don't want to work at high frequency. So based on that, we can check that which are the blocks that needs heavy computation, and which are the blocks that are running on very high frequency and continuously providing the output, and which are the blocks that are not working at very high frequency and that are not required to give the output at every amount of time. So based on that, we can check that this voltage can run on high voltage supply, and this block can run on low voltage supply.
Mm-hmm.
So
Oh, okay.
this is how we will decide
Yes.
that uh, different power domain and different voltage
Mm.
domains.
Have you worked on the label shifter placement also? Label shifter? Have you done the label shift?
No, I have not done the level shifter, but like I know the basic UPF command for that.
Okay, fine, fine. Okay. Oh, you know about the island crossing issue? Voltage island crossing issue?
Uh, this issue we'll see generally in UPF. Just I want to confirm with you. Are you asking about that?
Uh, no, it is related to the power domain.
Yeah,
And
power
how
domain.
ED tools detect them? How ED tools detect them?
So, like you're asking me about the issues which we see in the UPF file.
Yes, 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 yes.
Uh, like I've not worked on the issues exactly, but as per my knowledge, like I can say that the level shifter issue, like we will see if, for example, if the level shifter is missing, a signal is crossing from one voltage domain to other voltage domain. If the level shifter is missing, then the UPF reports will flag that it will that missing level shifter. So these kind of issues we can see. To resolve that, we need to put one level shifter either from low to high or high to low, depending upon the design.
Okay, okay. So you know about inrush current? Inrush current, you know?
Inrush current
Inrush current.
inrush current is when we switch on the any block, any RTL block. If we switch on any RTL block, then it will consume a high amount of current to wake up. So that high amount of current is called the inrush current.
Okay, okay, fine. You know about clamp 20, clamp 21? You know about clamp 20 and clamp 21 is in
Yes,
isolation cell techniques.
yes, yes, in isolation cell. So isolation cell is used whenever you are transferring any data or signal from the gated domain to the always on domain. So in that case, if the gated domain is turned off, but always on domain, the signal is going in the always on domain as an input. So there will be, it needs some value, right? We need to provide some value. So for that, we will use the isolation. We will use the isolation cell, and the isolation cell will clamp the value as per the requirement. Either we need to one, either the signal should be one or zero. Always all domain should detect the signal as zero or one. So the isolation cell will clamp that value to either one or zero depending upon the requirement.
Okay, okay, fine, fine. How do you verify the clock getting functionality in RTL versus gate level?
Versus
Gate level.
gate level.
Yeah.
Uh, so I have not done the verification part for the
Functionality is just okay, fine. Okay. You have the
functionality.
idea? You have the idea. You have just have the idea.
Just like to verify the functionality of the clock gating, we can check the waveform. We can check that if the like whenever the clock gating is enabled or disabled, we can check at the corner cases that our clock is clean or not. Is there any glitches are coming or not? So we can check in that manner clock gating.
Okay. Okay, fine. So, if we exceed the clock getting, will it increase the power, or like it is possible also that it will reduce the power?
Exceed the clock gating means what?
Excessive, sorry, excessive clock getting.
Uh, can you please repeat if we use excessive clock gating?
Let me tell you again. Why can excessive clock getting increases power instead of reducing it?
So if we are using access like extensively everywhere we are using the clock gating, so there might be chances actually when we use clock gating, generally we want to reduce the toggling of the clock, and clock is the one of the major thing which consumes a lot of amount of power. So most of the time clock gating is beneficial for us, but sometimes if we are using too much amount of clock gating and the duration for the clock gating is very less. In that case, the clock gating cell ICG cell may consume little bit amount of power, and the logic itself may consume little bit amount of power, and as well as it will also contribute to increase in area also. So in
Hmm.
that manner, it might increase the power instead of
Okay,
reducing it.
okay, fine, fine. What are the glitches issues in clock getting, and how to avoid them?
So generally, the glitches, like while doing the clock gating, we can see the glitches when you are using normal AND gate for the just I will explain you with example. So if you are using normal AND gate for the clock gating like this, and this is the clock coming here like this. Now what happens if this is the input clock
Hmm.
and this is the enable, and now we want to do like this. So initially our clock, this is the output of the clock, this was 0. Now we are enabling it. Then what happens? This will go like this. This is our output clock. So here we can see that for a complete on cycle, our clock is chopped off. It is not one, right? So this is the glitch. So to this type of glitches we can see while we use the normal AND gate, but if we use ICG cell, so that we can get the glitch free clock at the output. So therefore these type of to avoid these type of glitches we use the ICG cell.
Okay, okay. You know about body effect. What is the impact of body effect on the leakage power and delay?
Body effect is generally body effect means we are biasing the body of the MOSFET by applying some positive voltage or negative voltage at the body of the MOSFET. We are biasing them uh, so that it there will be a change in the threshold voltage. So by varying the threshold voltage, uh, we can change the functionality of the MOSFET.
Okay, you there are two type of biasing in that negative, forward and reverse, right? Which you are telling about which one?
So in the body effect, We use both type of, we can use any like positive or negative. Negative biasing, if we are doing in that case, like the threshold voltage can be increased or decreased depending upon the negative biasing or positive biasing. We can use both.
Okay. Okay, fine, fine. You know about DIBL, drain induced barrier lowering, short channel
Uh,
effect, long channel effect.
yes, yes, I know, but I am not able to
Okay,
remember completely.
okay, okay, no, no issues. Why does the leakage dominant in FinFET technologies? FinFET, in leakage current in FinFET.
Okay. Because as we go towards the lower and lower technology nodes, um, in that the N channel becomes very short, and as the channel is becoming very short, a little amount of leakage current is also impacting in a large manner. So as the technology nodes decreases, and earlier, uh, the small amount of current, small the leakage current was very small as compared to our technology. But now, as the technology nodes are decreasing, so even the small amount of leakage current is also impacting our like MOSFET, and it is impacting our design. So this is the impact, and therefore we need to be very careful uh, when we are going to the lower technology nodes, because little amount of leakage current can also impact us.
Mhm. So how to reduce it?
So there are two techniques to reduce the leakage current. One is using the multi-VT cell, and other one is power gating. So whenever our block is not functioning, we can gate the power supply so that leakage current is reduced. Leakage current is reduced, and second one is using multi-VT cell. And depending upon the critical path, if the critical path is there, we need to use the high VT cell, so that uh, we need to, in the critical path actually, we need fast, we need signals to travel very fast at high speed, so that we use high VT cell, that we use the low VT cell, and in the non critical path we can use the high VT cell.
ओके ओके फाइन। अच्छा, हमने ये आपको एक्सेस दिया था प्रोटोकॉल्स का, वीडियोस का, राइट? आपने वो देखना स्टार्ट किया?
हाँ, देखना स्टार्ट किया है, अभी चल रहा है वो।
ओके, क्योंकि उस वो भी ज्यादा इंपॉर्टेंट है, उससे भी हम क्वेश्चंस आगे वाले इंटरव्यूज में पूछेंगे।
हाँ हाँ
ओके।
हाँ।
की कंस्टेंट इन यूपीएफ, व्हाट आर द की कंस्टेंट्स इन यूपीएफ? की कंस्टेंट्स बेसिकली व्हाट, क्या होता है उसमें, क्या क्या कंपोनेंट्स होते हैं?
सो उसमें कंपोनेंट्स होते हैं, लाइक यूपीएफ, लाइक बेसिक यूपीएफ कमांड्स, if I want to say, then we have create power domain, create one is create power domain, create supply ports, create supply nets, connect supply nets, and set isolation cell, set level shifter, set power switches, set retention cell. Uh, this Yeah, these are the different basic constraints or basic UPF commands, I will say, which are used in the volt low power UPF.
ओके ओके। यूपीएफ 2.0 एंड 3.0, दोनों में क्या डिफरेंस है? व्हाट इज द डिफरेंस बिटवीन 2.0 एंड 3.0?
That
आइडिया?
no, that I'm not aware about that.
ओके ओके, लेट मी सी द आंसर। Okay. Basically, better hierarchy, the use and power state. Okay. Basically, lower power.
Okay,
Okay.
okay.
Mm, okay. Okay. Mm. You know what PST, power state table? UPF
Uh,
में आता है।
yeah, uh, I've heard this term, but like I am not very much aware about that.
ओके ओके ओके, एटलीस्ट बेसिक वगैरह आप देख लेना, हम इस पे आंसर्स भी दे देंगे आपको, है ना?
ठीक है, ठीक है।
You know about power switches strategy in UPF?
The power switches strategy, like I know that the power switches strategy, it is used to create the power switches, and with the help of the power switches, we can we can gate the supply voltage to the block. So if the block is not functioning, we can use the power switches, and the power switch, if we turn off the power switch, the supply voltage will be cut down to that particular block.
Okay. Okay. Um, what is the impact of IR drop and EM on the low power techniques? Like how it affect the power? IR drop and EM, electro migration.
IR drop, if there are if the current is high, so I uh, so IR drop is basically like power drop is there.
लो
And
पावर के लिए अच्छा है या बेकार है? मतलब लो पावर टेक्निक्स के लिए इम्प्रूव करता है या खराब करता है?
खराब ही करता है ये।
खराब करता है। दो टाइप का होता है, स्टैटिक का आईआर ड्रॉप होता है और डायनेमिक होता है। सो
ओके,
दोनों में डिफरेंस क्या है?
स्टैटिक
डायनेमिक वोल्टेज या कंटिन्यू।
static means when the block is not functioning at that time, if we are facing IR drop, that is called static IR drop. And whenever the block is functioning, that time if we are getting the IR drop, it is called dynamic IR drop.
ओके। ओके। नहीं नहीं नहीं, एक में
अच्छा,
कांस्टेंट करंट होता है स्टैटिक में और डायनेमिक में स्पाइक्स होते हैं, स्विचिंग
ओके,
स्पाइक्स होते
ओके, ओके,
हैं।
ओके।
ओके। नेक्स्ट इज व्हाट आर द पावर ग्रिड चैलेंजेस इन एडवांस्ड नोड? ये तो हमने ऑलरेडी आपसे ले लिया है।
Hmm.
You know about the thermal effect? What is the impact of thermal effect on low power techniques?
No, I do not have
Okay,
any
okay,
idea.
okay, okay. Suppose your chips fail due to power sign off due to high leakage voltage. What are the steps you will take, especially in the RTL code? Suppose your power chip fails due to the high leakage current.
Okay.
So what are the steps you can take? और क्या क्या आप कर सकते हो अपनी मतलब डिफरेंट टिप से कोऑर्डिनेट करके क्या क्या कर सकते हैं आप उसमें?
So if the chip fails due to the high leakage current, at my level, what I will discuss with the low power team that how much amount of leakage current is there, how much amount of leakage current is there, and what are the limitations, and what is our the target value, why it is exceeding. So one thing, after the discussion with the low power team, we can put the power switches for the power. We can perform the power gating by using the power switches. We can put the appropriate power switches at appropriate levels so that leakage current can be reduced. Second thing, what I can do that identifying the what are the critical path and what are the non-critical path, and putting the appropriate different multi-VT cell. We have SVT, HVT, and ULVT. So there are different range of technology nodes. Like there are different range of multi-VT cell in the standard library. So we can use that different VT depending upon the which are the most critical path, which are the least critical path, all these things. These two things I can, and also one more thing we can do. We can also do the clock gating. If some blocks are not functioning for a particular amount of time, we can introduce the clock gating there to reduce the amount of power. If in the RTL level also, I will try to find out that where I can put the where I can see the logic, and where I can put the data gating. So data gating part also I will do. Anything related to frequency scaling and voltage scaling, that part also I can do. But if suppose if there is a DCBS block is already present and it is already taking care about that, then we cannot do much. But still, I can go through the design. I will verify that okay, where all we can do the voltage and frequency scaling if
Mm-hmm.
required. So these type of steps I will take uh,
Okay. Okay.
for that.
Okay. Okay. Suppose we have the very high, let's say high IR drop after the clock getting insertion. What are the steps you will take to debug it? High IR drop even after the clock getting insertion.
Okay.
What are the steps you will take to debug it?
After the clock getting, also if we are getting a high IR drop, it means um, first I will check that why this IR drop is increased. It is why this IR drop is increased and what is the cause for that. So I will trace down the signals and I will check what is the reason behind that. It is causing the high IR drop. If it is due to any logic or if it is due to the clock gating. So if it is due to the clock gating, it means it is consuming our IC cell is consuming the power. So I will check that if it is due to the clock gating or not, and if it is due to that, then I will talk to the appropriate team to resolve that.
Okay. Okay. Fine. Fine. Uh, a block consume power even when gated possible, when it is gated also. A block consume power, right? It
Okay.
is consume or not? It consume power or not when it is gated?
Gated means which gated? What
Like
gating we are
power
using?
gated or like any gated like power or
So
clock gating.
yeah, it depends which type of gating we are using. If we are using power gating, then it
Okay.
will not consume power, and if we are using clock gating, it
Like
will.
little power it will consume or not? Little bit power it can consume or not?
If we are using power gating, then
Even power.
no, it will not consume that time.
Okay. Okay. Fine. Fine. Okay. Let me see the answer also. This. Okay. Sometimes it can. Sometimes it can.
How it
Leakage
can?
path.
Yeah, if we
Uh,
suppose if we are using.
reasons it is mentioned like leakage path is there or improper isolation is there. Tension shell are active. These are the possibilities
Okay,
to discuss.
okay.
Okay, going to the next question. Timing fail after the multi VTT optimization. How to fix it? Timings fails after the multi voltage optimization. How to
Uh,
fix it?
yes. So in that case, if timing is failing, for example, if I will share my screen.
Yeah.
So if we have these are the launch flop and capture flop, and this is the clock. So this is the critical path, and here we will use low VT cell.
Mm.
Let's say this is setup slack. If I will write it down. Now here, if we see our T combo earlier, here some VT is there in this combo logic. Uh, so the cell we used here in the combo logic is having the VT. So now if it is failing, setup slack is failing, it means our setup slack is equal to, this is negative, right? So how we can improve this? The one way to improve is to reduce this part, right? If we can reduce this part, and how we can reduce it? By reducing the T combo logic, T combo delay. And so if now I am seeing this setup violation, how I can do it? I can change this VT cell here. First step, what I will take, I will ensure that this combination logic should be minimum. I will try in my RTL. I will try that whatever the combination logic output is there, it should use minimum amount of logic and minimum amount of this gates. First one is this that, and second one what I can do, we can change. This is a critical path. We can change this by lowering down the VT. If we are using S, SVT, it means the VT is low. VT is low. It means current current is high. Current is high. It means the delay is very less. Now, if the delay is very less, it means this data will go very fast from here to here. If this is it goes very fast, it means this delay what we are facing, this delay will come down, and if the delay comes down, our setup slack will increase. So this kind of techniques I can use to meet the timing and to avoid the timing violation.
Okay, okay. It have mentioned that you can add the buffer, insert buffers, and you can replace critical cells with the lower VT.
Yes. So this
Mm.
critical cell I have replaced with the lower VT. This we can do. We can other techniques we can use. We can insert the buffers here also. Uh, uh,
Yeah, yeah.
Not here. Actually, here we can insert the buffers. This part. So by inserting the buffer, this part, actually L2, we can insert the buffer. Sorry, not here. We can insert the buffer here. So it means we are increasing the L2 value, and this things will get increased. That part also we can do.
Okay. Okay, fine. What are the two? How to reduce the power without impacting the performance in a critical block? So tell me the two major techniques for reducing the power without reducing the or impacting the performance.
Performance.
Yeah, without reducing the performance, you want to
Okay,
reduce the power in a critical block without reducing the performance.
okay. So this type of technique is not possible actually. If we are doing anything, if we are reducing the power, there will always be a trade-off between power performance in area. So
Yeah.
if we want to do the power reduction, then either there will be a trade-off in either in performance or in area. So
So
there is
area we can do. So it is possible then without impacting the performance.
without impacting the performance.
Yeah.
Uh,
Area you can reduce, like increase or reduce, whatever you want.
okay, okay. Uh, just a minute. Let me.
So which is the best, like according to you, clock getting or multi VTT or frequency scaling or voltage scaling? Which is best for this question?
Yes. So I think this third one, multi-VT cell, by using the multi-VT cell, this is the one of the technique what I think that area will no, actually, just a minute. It will actually. Back the design.
So here they have mentioned that clock gating is the best technique for this, and the second technique best is multivariate optimization.
Okay,
Two techniques
okay,
are the major. Clock gating is the best technique here. Okay,
okay,
okay.
okay.
Going for
Yeah.
the next part. Uh, you know about power aware clock tree? How to design a power aware clock tree?
No, no, this I am not. I
Okay,
don't have any
fine.
idea about that.
Uh, okay. Explain the crosstalk impact on power consumption. Crosstalk, crosstalk.
Crosstalk part. Actually, that part is majorly handled by the PD team. So the
Yeah.
crosstalk is basically when a signal is going, there are the two signals which are going side by side, and if there is a spike or changes in the signal, one signal, then it may impact other signal also. Interfere
Okay.
can do the interference, and it can impact.
Okay. How does glitch power compare to switching power? Glitch power and switching power. You know the difference between this?
And yes, so glitch power, whenever there will be a glitch, so it will consume little bit amount of power, that is called glitch power. And the second one was what you told.
Switching power, switching power, switching
So,
power.
yes, switching power, if there is a continuous switching is there, so a lot of amount of toggling is there, so that switching is called switching power.
Okay,
The
which is
power
more? Switching power or glitch power can be more
switching power
generally.
will be more. Switching power will
Switching
be
power
more.
is more. Okay. Okay. Um, how do you estimate power early at RTL plus versus post layout? How do you estimate the power early at RTL versus post layout?
In early RTL, at the RTL level, we cannot estimate the power. Uh,
Toggle based method.
for that, to estimate the power in the RTL, first there are the different tools are there, which generally low power team will use, and the low
Mhm.
power engineer who
Okay,
are.
let me tell you the answer. Let me tell you the answer. At RTL stage method, they have mentioned toggle based. At clock stage, they have mentioned accurate switching and post layout sign off tools. So these are the techniques they have mentioned, right?
What are this? What is the toggle based that you are telling? What is the toggle based method?
Toggle based means you are basically a type of switching toggle based. Let me check because I have also not used it anywhere, but it is mentioned. Low power. Yeah. Basically, enabling and enable and disable different components and all, right? That they have mentioned. Or it is a type of switching also. Right? Enable and disable you have to do of different component at RTL stage. And gate is actual switching, actually you are switching it. And post is we have the sign off tool. Okay, what are the limitations of ED tool in low power techniques you have faced? What are the different limitations you have aware of at the art at the EDA tool?
EDA tool. Actually, this EDA tool will. It depends upon the what EDA tool you are using, and what is the functionality of that EDA tool, what you want to do. So basically, this EDA tool, the people belonging to the CAD team will tell. The people who are extensively working on EDA tool itself. This is not very much related to RTL people.
Mhm. It is have mentioned that accuracy versus runtime trade-off, power intent complexity, and limited timing word modeling. Accuracy and runtime you can mention obviously, right? Right. So yeah.
Yeah,
So
but
these
yes,
are some of the questions sometimes they ask, right?
correct,
But
correct. Yeah.
these are the
So
very
mostly,
like
yeah.
PD questions also. Here we have asked some of the PD also, right?
Okay, okay. This is basically this one EDA tool related things are there which
Uh-huh.
EDA people will know, and it is not related to RTL and ED people.
Okay, 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 okay. Okay, you have three power domain, point 0.8, 1 voltage and 1.2 voltage.
Okay.
So where you will place the lever shifter?
I will place a level shifter in between point 0.8 and 1, as well as 1 and 1.2,
Okay,
and as well as between if both all the three are interacting with each other, we need three level shifter at the output of point 0.8. It means in between the point 0.8 and 1, in between point 0.8 and 1.2, in between 1.2 and 1.
okay. Why we place the lever shifter near the receiving domain, not the source?
It is not like that we can place anywhere. If we want to place the level shifter at the source also, we can place near to the source, and if we want to place near the receiving destination, there also we can place. Our like main goal is that the signals which are going from one power domain to other, they should pass through the level shifter.
Okay. Where does the most power goes in AI chips? Most power. Like where does the most power goes in AI chips?
So most of the power goes into the clock. So if the clock is continuously toggling, it will go into the clock. Yes, most of the power will go here, and like if any heavy computation is going on, if there are
Yeah.
some blocks which are performing heavy computation tasks, so that will also consume lot of amount of power.
Okay. Okay. Fine. 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 If I add the clock getting everywhere, will the power always reduce?
It depends. If we can only use the clock gating whenever we want to, whenever any block is not functioning. There only we can add the clock gating. We cannot add it everywhere. If we are adding the everywhere clock gating, it means uh, the functionality should be there. Like what is the functionality of the circuit? If everywhere we are adding the clock gating, it means most of the chip is not functioning, right? So we cannot do like that.
Okay. 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 In silicon, a block is clock gated, but is still consuming power. So I have already told you the answer. Tell me the
Can you
answer.
please repeat once?
A block is clock power gated. Power it is power gated, but it is still consuming the power. It is possible.
Yes, it is like if um, we have not
Leakage
done
current
proper leakage current. To reduce the leakage current only, we use the
or
power.
some two methods also I mentioned previously. Improper retention. Okay,
Yes,
then
that,
fine.
yeah, that is actually if we have not properly applied the gating method, then issue might come. If we have already properly applied, then issue will not come like that.
Yeah, yeah. Okay, fine. So you know about DVFS?
Yes, DVFS means dynamic voltage and frequency scaling. It
Yeah,
is
correct.
yes.
What are the major challenges they face? What
So
are the
major
more challenges? Yeah.
major challenges they face, like if the FSM triggering is correct or not. First, like
Stability.
there can be major challenges depending upon the functionality and what what is your intent. What are you doing? What do you want to do? First one is like if the triggering is properly or proper or not. If FSM, what are the different uh, power operating modes? What are the different operating modes? What are the different value of voltage and frequency?
Basically, the stability, right? How to control it, controllability, right?
Yes, yes, controllability, and also we need to check all the functionality that in terms of challenges, if the DCBS is triggering at the proper condition or not, is there any false triggering or not, and suppose if the request came to change the voltage or to change the operating mode, so it is accepting the request or not, and it is informing to the other blocks that I have accepted the request. If not, then our timer is activated or not, that timeout counter is activated or not, and if the operating mode has been changed, so at that point it is informing to the processor as well as other blocks that the operating mode has been changed or not. So these type of things we need to take care, and if it will request the clock controller and voltage controller to change the voltage and clock depending upon the new operating mode. So it is requesting at the same particular moment or not, the requesting condition is proper or not. So all these things we need to check.
Okay, 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 fine, fine, fine. Yeah. So this is all about this round. So next round we
Mhm.
will. So yeah. So it was good,
Yeah,
na?
yeah, it was good.
Yeah. Sure, sure. I got your
Okay.
point. Okay, fine.
Yeah, yeah.
Thank.
Okay. Thank you. Thank you.